Okay, good afternoon, everybody. So today there will be a talk by Professor Somobrata Acharya. Uh, Before the talk, I would like to introduce or say a few words about Professor Acharya. I actually got introduced with Professor Acharya through Professor Manas Mukherjee, and so uh, he is presently a senior professor in School of Applied and Interdisciplinary Sciences, Indian Association for Cultivation of Science, Jadavpur. He has many publications in international journals. He edited book chapters also and uh, has about 8 patents. So he also worked as a researcher in Japan and Israel. Presently, he is working in different kind of synthesis of various step-controlled nanoparticles. Mm, He also proposed hierarchical dimension-controlled assembly of nanowires and demonstrated successive coalescence of nanowires into single crystalline 2D seeds. So I'd like to invite Professor Acharya uh, to deliver the talk.
So thank you very much, Tanmay, for your nice and kind introduction. And good afternoon, everyone. And I would like to extend my thanks to also Professor Manas Mukherjee for giving me this opportunity to show some of my work in this esteemed platform and is such a nice international institute. So I framed my talk in like this way that the assemblies of nanomaterials and molecules at the water surface. That means that whatever I will show, that will be based on the water surface. And yeah, so before that, this is the field up area of our group. We're working on the synthesis, assemblies, and applications of the nanomaterials, crystals, and molecules, depending on their properties, actually. So we are mainly focusing on the size and shape controlled ultra narrow nanomaterials. They are controlled two-dimensional and three-dimensional assemblies, both for the nanomaterials and molecules. Their junctions, these junctions can be type 1. Sorry. Yeah, I can hold it like this. Yes, certainly. But somehow this pointer is not focusing here as it should be. It is focusing here, but it's not. So I can show my with my hands. Okay. Yeah. Now the voice is coming. Is clear? Okay. Perfect. So type 1 and type 2 kind of junctions. These are not the regular junctions. Junctions at the very tiny scales. And of course, depending on the properties, we are putting these molecules and nanomaterials or materials in energy harvesting and power conversion applications. So I frame this talk in 3 different categories. First, I'll show the monocomponent and junction nanocrystals and how to probe the junction at the nanoscale. Then the assemblies and successive coalescence dimension control on the water surface with the one-dimensional nanocrystals. And then some new concept which has been introduced recently. This is called aggregation induced emission because the molecules are usually losing their luminescence in the solid state. So for device application, we need some molecules which are working and giving high luminescence in the solid state. So that is called the aggregation induced emission. So I'll show the how to form these two-dimensional crystals of these molecules and the mechanism why are they giving such intense fluorescence which is not available yet, and possible device applications with the nanomaterials and molecules wherever it is applicable. So the first topic, monocomponent and junction nanocrystals. So you all know this is very established now that this nanocrystal shows size dependent properties. That means if I change it to bigger to smaller, I can change the band gap. Eventually the color can be tuned. And also the electronic properties of the nanomaterials can be tuned using by changing the shape of the nanocrystals. For example, this bulk 3 nanocrystal is usually giving continuous density of states. For zero-dimensional quantum dot, which is confined from all 3 dimensions, that is giving delta-like function. The one-dimensional words, they are giving spike-like functions, and the 2-dimensional sheet, they are giving the staircase-like density of states. So it all depends that how these charges are confined from all dimensions. So this is basically called the band edge tuning, and following that we have worked a lot with a vast variety of nanocrystals there. For example, we have prepared nanocrystal which is zinc sulfide. Is the diameter is only 1.2 nanometer and length is only 5 nanometers. And look at the super fine supercrystalline assembly of these nanocrystals there. Each and every black line is basically representing one single zinc sulfide nanorod. Similarly, this is other composition using zinc selenide. So here diameter is slightly larger, 1.3 nanometer, and length is slightly shorter, 4.5 nanometer. But again, we can put them into supercrystalline assemblies there. So not only that, we can design the ultra narrow nanowares with much longer aspect ratio. This is the example that lead sulfide nanowares. The diameter is only 1.8 nanometer and length is exceeding at least 200 nanometer there. Also, this is the cadmium sulfide nanowares. This is also 1.3 nanometer in diameter and more than 100 nanometer in length. And we put them into different kind of device application based on those properties. So this is the control of the band gap. But if you really want to show the effect of the shape, you have to work with only one material and you have to design different shapes there. So we have also done that. This is an example for the lead sulfide quantum dot. So we designed zero-dimensional quantum dot, one-dimensional rods, and two-dimensional sheets here. And we showed that how the degree of confinement depends on the dimensionality of the materials, and it depends the zero-dimensional is highly confined, one-dimensional nanomaterials are intermediate, and two-dimensional nanomaterials are more relaxed. So these were the cases for the monocomponent quantum dots. Very interestingly, if you adjoin two monocomponent quantum dots together, you'll be getting different kind of electronic properties, which is completely different from the monocomponent quantum dot. So this we call coupled quantum dot here. So for example, this is one semiconductor quantum dot, this is another semiconductor quantum dot, and you form an interface of these two quantum dot, and the interface will be the determining factor. The individual properties of this quantum dot will be completely lost there. Another advantage is that for monocomponent quantum dots, there will be size distribution of shape distribution effects there. So that actually leads to the energy transfer within the ensemble of this quantum dot, and this can be highly prevented by using this coupled quantum dot, because the resultant properties of this coupled quantum dot will not be dependent on the individual quantum dot, rather it will be depending on the junction itself. Let's see how it happens. So we form the coupled quantum dot using two different quantum dots here. One is the zinc selenide, the other is the cat sulfide. And this shows the transmission electron microscopy picture showing two different components. These two are in also two different crystallographic phases. So these are the optical properties of the pristine quantum dot for zinc selenide and cadmium sulfide there. But very interestingly, if we adjoin them together, the individual properties of these quantum dots are completely lost, and instead a new transition band gap can be generated. And this new transition band gap is of course controlled by the extent of the interface. That means if I make the interface more diffuser, so one can tune the position of the transition gap by means of the extent of the interface. So by this way, one can usually tune the band edge engineering. So these are the controls with the quantum dot there. So if the interface is determining the entire electronic property, so it's very important to probe the interface there. But how would I probe the interface at the local scale when the entire dimension of this coupled quantum dot is 5 nanometer? So we took the help of STM. Of course, STM expert is sitting here. So we started to take the spectroscopy across the junction at different points. So this is called the DIDV spectroscopy. And from this DIDV spectroscopy, we found the position of the conduction band and valence band. So at each point is giving the position of the conduction band and the valence band there. And we can eventually calculate the band offset, which is the difference between the top of this conduction band and bottom of this conduction band of the other semiconductor, as well as valence band. So we found the band offset is 0.3 electron volt for the lower level for the HOMO and 0.4 electron volt for the LUMO there. So this gives you immediately the idea that this is type 2 interface. But when we look at the band positions, energetic positions, we found that actually is not perfect type 2 interface there. So what is happening here? Because this point should be lower, much lower in case of perfect type 2 interface, but is residing somewhere on the top. So we started to look at this interface issue, that why it is happening. So if we have perfect interface, where the atomic diameter of both the components are same. So in that case, the interface will be perfect, there will be no strain. But now if we have difference in the atomic radii of these two different components, so one component will be facing the compressive strain, the other component will be facing the tensile strain, depending on the diameter of the atoms. So the band gap for one component will be opened up and the other component will be squeezed. So as a result of that, the junction will be abrupt because the strain of the interface is huge there. So what we'll do then? How to reduce the strain? So the interface will always try to make a kind of alloying there. So that will basically reduce the strain of the interface, and in that case, you will have a smooth interface there. So this actually happened in our case. So we really proved that the interfacial strain is relaxed by means of this alloy formation, and we have a deviation from the actual type 2 interface. Rather, we are finding quasi-type 2 interface there. Fine. Further, we engineered the band gap. We fixed one size of the quantum dot constant, and we varied the other size of the quantum dot systematically. So this fixes the band gap of one component and varies the band gap of the other component very selectively. So that's how we can control eventually the band offset in the conduction band and valence band, and of course the transition gap just by tuning the sizes of the component. We can create more complex junctions. This we call the superlattice. So this is consisting of two different semiconductors arranged in alternative waves. So this is of zinc sulfide and cadmium sulfide. The length of the zinc sulfide is 5 nanometer and the diameter of the cadmium sulfide is 2 nanometer there. So we can synthetically design such superlattice systems, and once you have such kind of superlattice system, you'll have array of quantum oils. And since this is at the nanoscale, each and every quantum oil can talk to each other, right? Because the distance is only 5 nanometer there. So as a result of that, you can get a very full, very narrow width at maxima, something at the 25 or 26 milli-electron volt at room temperature. So this is basically comparable to laser length. That means you can find a single laser nanowidth there. What else we can do? We can basically tune the spacings of these two different components by ligand chemistry. We can use different length ligand to vary the spacing, and eventually we can tune the position of this lacing in the visible range. So those were the with the junction nanocrystals. Some glimpse with the other nanocrystals which we are doing. All these are unpublished. So a large variety of perovskite nanocrystal we can create. You can see the beautiful distribution of these nanocrystals here of different, some are cubic, some are one-dimensional nanowires, some are hexagonal. So all these things we can do in our laboratory synthetically. So not only the nanocrystals, we can also design the single crystals of different shapes. So these are the examples of all these single crystals. Some are in perfect hexagonal state, some are layered single crystals, some are one-dimensional single crystals, some are square single crystal, and all of them are containing different optical and birefringent properties. So, story 2. Nanomaterials at the water surface. So indeed, we have invented this technique. There are several assembly techniques there, right? So one is spontaneous assembly. There's a self-assembly. The other one is the directed assembly, where the external force is required. But here, in the self-assembly, you have different categories. Either it will be driven by the van der Waals forces, electrostatic interaction, using linkers, dipolar interaction, or drive-mediated assembly. All these things can be happening. And for directed assembly, you need some external force like electric field or magnetic field or spin casting or use of the templates. But one technique which was invented long time back in 1932 is explored in a very little for the nanomaterial for this kind of assemblies. Well, liquid-liquid interface is very well known, right? Where one can have the reaction at the interface of two different liquids, but you don't have control at the interface. But this technique is called the Landau-Blogger technique. It gives control of the surface pressure, which is very important to induce some kind of reaction or to control the spacings between the nanocrystals or to align them. So this allows to do it at the air-water interface. And this is actually very much applicable for the classical amphiphilic molecule consisting of hydrophobic and hydrophobic groups. So once you spread them at the water interface, the hydrophilic group will be interacting the water, whereas the hydrophobic group will be staying apart from the water there. So as a result of that, you can form a nice monolayer of the amphiphilic molecules. But our nanomaterials are not amphiphilic. They are coated with some kind of ligands which are hydrophobic in nature. But still that works because it mimics a timber lock there. So it will just float at the water interface and one can do a very controlled compression of these one-dimensional nanomaterials at the water interface there. Another advantage is that after alignment or after assembly formation, one can transfer this monolayer on solid substrate and one can deposit the three-dimensional stacking of this one-dimensional monolayer there. So I will show all these examples here. So our journey started with these zinc sulfide nanorods, which are 1.2 nanometer in diameter and 5 nanometer in length. So after synthesis, we spread these one-dimensional nanorods at the aorta interface, and we started to lift up on the transmission electron microscopic grid and followed the stages of different compression. So at the very beginning, when the compression is low, we found that these nanorods are remaining in small domains, and there is a big distances between the domains there. So once we started to compress it furthermore, we saw that all these domains are basically aligning along one dimension. So this transmission electron microscope image is showing that indeed these tiny nanorods are aligned over large area on this scale. Very surprisingly, if we keep the surface pressure at certain point, we found that within this aligned assembly, some of these nanorods are coalesced into small length nanowires, whereas the rest of the nanowires are remaining in the aligned form. That means we can induce some kind of end-to-end coalescence of these nanowires there. So at this point, we thought, okay, let us give some amount of energy in the form of heat to this monolayer. So we just heated it just above the ambient temperature at 40 degrees Celsius, and we found that all these nanowires are basically merged into nanowires retaining the same 1.2 nanometer diameter. That means we can induce a coalescence reaction to make the nanorods into nanowires retaining the same diameter, which is pretty interesting. So if this work for the nanorod to nanowire conversion, it should also work for the nanowire to nanosheet, two-dimensional nanosheet conversion. So we have done that also. In this case, we have chosen lead sulfide nanowires, which are 1.8 nanometer in diameter. Length is exceeding here over at least 200 nanometers there. So again, we spread at the air-water interface and did the same thing. First, we align these nanowires in one dimension. These are the successive TM images taken from the same area. This 0.1 is actually 0.1 in this frame. This 2 is actually 0.2 in this frame. So in this way, we can align this one-dimensional nanowires over 15 microns square, which is a large area alignment, and the pitch, which is a center to center between the adjacent nanowires, is only 2.8 nanometer here. That means the ultra high density alignment of this nanowire. So again, we gave some amount of heat to this water surface, and we found that all these nanowires started to form nanoribbons of 8 to 10 nanometer in diameter. So after that, if we keep this condition on, we can really make a complete two-dimensional semiconductor sheets of lead sulfide. The diameter of these sheets is exceeding 200 nanometer, 200 to 250 nanometer there. And also we can have kind of alignment of these two-dimensional sheets on this surface. So this is the atomic force microscopic image here. So these two-dimensional sheets are completely single crystalline in nature, as one can see from the high-resolution TM image diffraction. And we also found some tildes at the edges. This comes in order to give stability to this two-dimensional structure. So now we started to find out that what is the thickness of this two-dimensional sheet. Note that all these nanocrystals are basically coated with the ligands from all surfaces. So we'll have ligands on the top, we'll have ligands at the bottom, and then we have a semiconductor sheet like this. So once we are measuring the thickness, the AFM technique counts the entire thickness of the organic as well as the inorganic. So we found the entire thickness is to be less than 5 nanometer. Now if we count the geometric length of these ligands on the top of the surface and the bottom of the surface, eventually you find the inorganic core is less than 1.8 nanometer there. So which is pretty thin, because the graphene, this time single layer graphene, is something like 0.5 nanometer in thickness. Fine. So we now started to find out that what is the activation of this, activation energy of this coalescence reaction. This is important. You are inducing some kind of reaction at the air-water interface. So we have done that. We allowed the experiment to be done at different temperatures, allowed to compress the monolayer, and from there we find out the rate constants at different temperatures. So you can see very interestingly that up to 40 degrees Celsius is showing a single component decay. But once we are exceeding 42 degrees Celsius, we have two different components here. So that means this is not very straightforward coalescence process. So we plot the rate constant versus temperature plot, and from this slope we can eventually calculate the activation energy for this coalescence reaction, and we have carried out for two different cases, below 42 degree and above 42 degree. So we found that below 42 degree, the activation energy required is 10 kilojoule per mole, whereas in case of 50 degrees Celsius, we need the activation energy of 53 kilojoule per mole. Now, what is this activation energy? This activation energy is nothing to dislodge an organic molecule on the surface of the nanowires. So in order to prove that, we also calculate the density functional theory calculation here between the previous dimer and the ligand, which is an amine in case of real nanowires, and we calculated the binding energy to be 50 kilojoule per mole. That means this activation energy is sufficient to induce the reaction at the air-water interface, and one can dislodge these molecules from the air-water interface by means of just slight external energy. No, actually, that is simple calculation, timer and the organic. This is important. Why I will come later, because water dipole moment is also important parameter. Yeah, that's something. Yeah, so I'll come to that. So from this slide, possibly it starts. Okay, so we found that the pristine lead sulfide nanowires were in cubic system, cubic crystalline system. So that has a zone axis of 0, 1, 0. Okay, and the nanowires, so that is bit tilted to 63.44 degree, the zone axis for the nanowires. But for the two-dimensional shades, the zone axis is deviated by 18.43 nanometer. So it is straightforward coalescence process. One might have expected that these zone axis of the cubic system will remain the same. So it is not happening, the zone axis is changing. That means the crystallographic orientation is changing there. So why it is changing? So from this schematic, I can explain it that if this is the direction from where you are seeing the diameter of the nanowire, right? And you have the ligands all around. So those ligands which are remaining on contact with the water surface, they are getting the heating first, right? But the top surface, top carpet is remaining intact. So as a result of that, once you have started to heat this water surface, so these ligands which are at the contact of the water surface, those will dislodge first. And the top surface will remain intact. As a result of that, there is a induce of the twist of this. So that actually changes the direction of the zone axis. So once you are cooling it down further, so these ligands can further absorb to the bottom surface to impart stability to this two-dimensional structure. Okay. Yes, because the top surface is remaining, it is not getting heat. Only the bottom surface is getting the heat. So that's why it's a, I mean, it's not getting the heat is wrong statement. It's also the getting the heat, but is getting lesser heat. The gradient is there. So now the question comes that where this released ligands goes. So for that, we again have taken the microscopic evidences. These ligands are basically hydrophobic in nature. So they has to be within these two-dimensional shades. So we found that yes, some of these ligands are really can be seen along with this two-dimensional shade. So these are the ligands which are released actually from the surfaces of the two-dimensional shades there. Now we have compared the actual measurement of the band gap of the nanowires as well as the two-dimensional shades there. So this is not the regular absorbance, this is measured across the air-water interface by means of fiber optics. So we found the band gap of the nanowires to 2.03 electron volt, and for the two-dimensional states is 1.82 electron volt. That means the band gap is reduced because of that change in the dimension rate. So we compare that with the density functional theory. Actually, you also have seen a similar kind of trend. The nanowire is showing something like 2.14 electron volt in comparison to 1.8 electron volt of the two-dimensional states there. So once you have fabricated a large area two-dimensional sheet, it gives you the opportunity to fabricate electronic devices there. So we used electron beam lithography to put or pattern electrodes on top of that, and we measured the transport at different temperatures. So you can see the current is increasing with respect to temperature, which is characteristics of the semiconductor system. Also, resistance is changing, and it appears to be in the kilo ohm region. Okay, so this proves this is completely semiconductor in nature. Further support comes from the transport measurements at 60K, and comparison with the calculated transport is also gives in the same order there. So we can claim that we have designed a very thin, large area semiconductor sheets with this interfacial technique. Now we compare with the graphene. Graphene has four orbital electrons, right? So three of them are forming the sigma bond. One is forming the weaker pi bond, making graphene a very good conductor there. In order to find out such possibility exists in our two-dimensional semiconductor sheet, we have also calculated the different orbitals charge distribution, and we found that some of these orbitals are really giving continuous charge distribution above and below the nodal plane. So what will happen if this kind of things are overlapping together? So this overlapping basically will lead to some continuous charge distribution, which can show the enhanced conductivity there, right? So this is the reason for the enhanced conductivity. So if this work for making the one-dimensional nano rod to one-dimensional nanowires and one-dimensional nanowires to two-dimensional sheets, we can also draw the pattern using the same technique. Because the direction of the dipping will determine the direction of the alignment on the solid support. So we have carried out that one for zinc selenide nanowire. Again, we have formed a large area aligned assembly of these tiny nanowires. And then after formation of the assemblies, we deposited the second layer in a different direction. So this can give you the cross direction, or yes, just you need to change the direction of the dipping. No, it has to be dried. So once you dry that one, then you can form a layer by layer assembly with ultra high density junctions, right? So we have demonstrated that, and in this case, we found the junction density to be 60 multiplied to the 3 per micron square. Fine, third and last story. So basically, as I told in the beginning of my talk, that aggregation induced emission is a quite new observation. People worked a lot with the luminescence. People have tried to put the organic molecules for device functionality, but again, it works very good in solution, but luminescence quenches in the solid form. But all the devices which you are making basically, so that works in the solid form, right? So another challenge is that conventional light sources which consumes a large amount of generated energy, those are to be replaced by the solid state lighting, that is light emitting diode, something like that. So along this line, this concentration quenching phenomena is quite detrimental. If you take one molecule which is highly luminescence in the solution form, you make it in the aggregated form that mimics the solid form, then you will find the aggregation is completely quenching, right? You won't have any kind of luminescence once it is in aggregated form. But there are other classes of molecules. We show the opposite phenomena. This is called the aggregation induced chains. So what happens here? Here, in solution form is non-emissive. But once you are basically inducing the coalescence, the aggregation, you are getting very high degree of luminescence there. Okay. So why it happens? Because one class of molecules is performing pi stacking. Okay. The other class of molecule, if you look at the structure, you have a spiral scatter at the center. And you have 6 lanes which can rotate freely in the solution form. So once they are rotating in the solution form, you have non-emissive pathways open up. So if you stop this rotation of the spinel rings, automatically what will happen? This radius dip channel will be opening up. As a result of that, this molecule will become luminescent there. There are two tentative, again I mentioned, two tentative mechanism for that. One is the restriction of the intermolecular rotation, another is the restriction of the intermolecular vibration there. But all these are very qualitative. Okay, so people have tried to put this aggregation in solution phase by increasing anti-solvent. For example, you have got a good solution, you put water there, so you increase the water fraction. As a result of that, there will be aggregation of these molecules. So then you'll be getting, again, good AIU effect. People have tried to put it in powder crystalline form or forming single crystals, making polymer blends of this AIU gel, putting them within the layers of materials or even biological cells to put the aggregation of these AI agents there. None of the techniques are basically giving you a good control over the state of the aggregation. And if you won't be able to control the state of the aggregation there, the photophysical properties cannot be tuned or controlled, okay, which is a requirement to make a good lighting device there. So we again adapted the same technique. We have taken variety of AI gel. Again, look at the structures of these AI gel. They're basically hydrophobic in nature. So these hydrophobic molecules are not supposed to float at the air water interface, but they will form a quite nice monolayer because of these hydrogen bonds with the water molecules, and of course the benzene ring and pi electron clouds interaction there. So as a result of that, they will form a quite nice monolayer there. And we utilize this property. We first have chosen a cyclometallic iridium 3 complex there. We spread that, this is the molecular structure. We spread that at the air water interface. And look, at the very beginning of the compression, they are forming two-dimensional crystals there. And the height of the two-dimensional crystals is below 4.5 nanometer. Now we started to compress these monolayers of these two-dimensional crystals and see that with increasing surface pressure, these two-dimensional crystals are aligning in a single direction there. But in any case of stage of compression, the height is remaining the same. That means the crystals are not overlapping. The monolayer structures remains at the aorta interface. And in each case, this height is around 4 nanometer there. Interestingly, in solution form, this gives absorbance which is larger than the two-dimensional crystals. But once we are taking the fluorescence, the fluorescence is multiple times higher than the solution here. Okay, so this green curve is showing the solution fluorescence, and these are for the two-dimensional crystals taken at different surface pressure. So we measured the quantum yield of this solution and for the two-dimensional crystals there. We found a rapid jump in the quantum yield. The quantum yield increases from 1% to 34 to 39% for the two-dimensional crystals here. And in according to that, you can have the confocal microscopic image, which is giving the green luminescence because you are getting the fluorescence spectrum in the around 500 nanometer there, right? Another point is that we have measured the fluorescence lifetime. The solution form is giving lifetime of the order of nanosecond, whereas this two-dimensional crystal is giving very long lifetime of 2.26 microsecond. So there is a jump in the fluorescence lifetime there. And of course, you can increase the luminescence but more by making the stacking of the two-dimensional crystals in three dimension, right? But look, even if you are increasing the stacking, the luminescence quantum yield is not increasing a lot. It's remaining in the same range. So this is very interesting phenomena which I'll explain later. So what happens? Again, now we compare the packing density obtained from the AFM image, we found that the surface coverage, that the packing density is increasing with respect to the surface pressure. But if I compare the PL, PL is remaining of the same region. That means surface density is not affecting the PL there. Okay. So then we compared that why it is happening. We started to look at the photophysical processes. Before that, we have taken the fluorescence spectrum, the photoluminescence spectrum at 77K, that is at low temperature. Why 77K? Because at 77K, you'll have the freezing of this vibration, right? So it will freeze the molecule furthermore. So that was the plan. So we have taken that one, and very surprisingly, we saw that the two-dimensional crystals giving the same luminescence intensity as we obtain at the 77K, and the band positions are remaining at the same position. So this is again pretty critical. At 77K, whenever we are getting some kind of luminescence spectra, it belongs to phosphorescence. So phosphorescence, if we look at this schematic Jablonski diagram, so once you have the absorption and it comes down, it gives you the prompt fluorescence. Now, if you have an intersystem crossing to some triplet, and if the singlet triplet gap is small, it can come back to the singlet again and give you the fluorescence, which is called the delayed fluorescence. And if the decay occurs from the triplet state to the ground state, it gives the phosphorescence. So from here, one can readily see that phosphorescence should occur at the longer wavelength than the prompt fluorescence or delayed fluorescence. Fine. But in this case, we are finding that the position of this photoluminescence is remaining the same. So it gives rise a question whether it's a process of delayed fluorescence or phosphorescence. That's one point. Second point is that what is the origin of this intense fluorescence? We are dealing with the same molecule. We are making the two-dimensional crystal, and we are finding that the fluorescence is really increasing. Second thing, that what is the origin of the long fluorescence nighttime? So this, in order to prove that, we have done some critical experiment with synchrotron radiation at the air-water interface there. Okay. So during this compression stage, we started to measure the in-plane and out-of-plane diffraction there. So what's this in-plane diffraction? It gives a change in the intensity of the diffraction peaks, retaining the same peak position. And if you compare these images all together, you'll find that the one peak intensity is remaining the same, whereas the intensity of the other two peaks are changing with respect to compression. So this means that these two-dimensional crystals are aligning and move in one direction, okay, from other two directions. Then out of plane diffraction, it gives a different thing. The QZ component is basically giving the 2-0 reflection is remain the same, whereas the 1-1 and 0-2 reflections are changing with the compression. So this implies, sing it. That is 4 nanometer. 4 nanometer. Yeah, 4 nanometer. Otherwise, it's very thin. QZ component will be there. So what it gives, what it implies then? It implies that this 2-0 plane is remaining along the length of the two-dimensional crystals. Okay, and other two planes are along the diagonals. Fine. So from here, once you measure this kind of critical, why I'm mentioning that is critical experiment, because it's a dynamic system at the aorta interface. Simultaneously, you are measuring the diffraction using synchrotron beam. So it's really critical, and specialization is required for this. But anyway, from this measurement, we can find out that this spacing for these cases. So for these three planes, we find out that this spacing to be like this: 12 angstrom, 9 angstrom, and 7 angstrom there. And once you have the determination of this spacing, eventually you can fix the unit cell of these two-dimensional crystals. And we found it to be centered reticular unit cell with lattice constant of 19.28 angstrom and 14.96 angstrom and space group is C2 mm. Okay. So once you have this kind of information, now question comes that what are the interaction there? So in order to find out the interaction, we arrange these molecules within these unit cells in different patterns to find out that what are the interaction there. We found that a number of CH5 interactions are dominating within these two-dimensional crystals. Those interactions, the pi-pi interaction, which was quenching the luminescence, is missing here. So that's the reason is giving high photoluminescence in the solid state. So now we need to confirm that this unit cell, what we have modeled is perfect. We compared the generated in-plane diffraction with the measured in-plane diffraction there, and it closely matches, suggesting that this unit cell is truly designed, and repetition of this unit cell in 2 dimension will form these 2D crystals there, right? Another confirmation of rigidness of these molecules within 2D crystals comes from the FTI measurement using 2-dimensional detector. So we compare the powder and 2-dimensional crystals there, and we monitor the iridium-hydrogen bond. So you can see there is a shift and sharpness in case of 2-dimensional crystals, which readily proves that these molecules are tightly arranged within these 2-dimensional crystals there. Then we took the help of the theoretical calculations in order to prove the enhanced spectroscopy purpose. So we first take the energy eigenvalue and charge distribution for the monomer, and we found that the charge distributions are around the iridium and phenol lighters there. And then we plotted the energetic position for the singlet and triplets, and also we found out the spin orbit coupling. Spin orbit coupling is extremely important parameter here, because if you have the inter-system crossing, you need to have a stronger spin orbit coupling, right? So after that monomer, we have taken the dimer there, and we have calculated the same, and we found that some of the states and singlets and triplets are very closely residing, giving a very small singlet triplet gap, as well as we can find out the spin orbit coupling between some of the singlet and triplets. They are very strong. So this allows you the opportunity for the inter-system crossing. So now we plotted, I'm counting that. Of course, that point is included here, because I want to distinguish between the delayed fluorescence and phosphorescence. So yes, right. So in case of delayed fluorescence also, you need these 2 parameters: strong inter-system coupling and small energy gap between the singlet and triplet. But how would you exclude that one? That I'm coming here. Now we plotted the compared the singlet monomer and dimer cases. Dimer was actually made following the initial structure there, and from here we can see the obviously the number of singlet and let's say the increasing a lot. I'll finish quickly. And the effective splitting, which is the difference between the singlet and triplet, is reducing further for the dimer. But important point to note, the position of the lowest triplet is remaining the same both for the monomer and the dimer. That means this singlet triplet gap is the same, even if you are increasing the number of molecules there. Okay. So now we compared this gap, theoretical gap between the triplet, lowest triplet, and the ground state, and this readily comes in the same position of the luminescence what you find out, right? So this photoluminescence is basically pointing out that it originated from the triplet state. Okay, that's one point. Now coming back, that how do you exclude the delayed fluorescence there? If you look at the position of the lowest triplet, okay, it resides much lower than the lowest singlet state. So this prevents the possibility of the inter-system crossing to the singlet that will give you to the delayed fluorescence. Okay, so we exclude the possibility of the delayed fluorescence by means of big singlet triplet gap. In order to confirm this, furthermore, we have carried out the experiments by varying the temperature, and we have varied the temperature from 20K to 360K, and we measured the photoluminescence there. Even in that process, it should have changed a lot, right? Because the charge carriers has to come back to the similar state. But we found a decrease in the photoluminescence intensity for this when we are increasing the temperature there. That means it is from the same state of origin, and furthermore we have taken the radiative decay curves at different temperatures. And within this temperature range of 20K to 360K, we can see the decay is even of the same order, right? It's not changing a lot. It's from 5 to 10 microseconds. That means it is originated from the same triplet state, excluding the possibility of the decay fluorescence there. Then further we extended the calculation, we found the two-dimensional sheets there, and then we calculated the density of states, both for the singlet and triplet. You can see that the band gap is comparable in both the cases, and the number of states have increased a lot, giving rise the possibility of this inter-system crossing, as well as more number of charge carriers to be involved in this process. So this actually explains that once you are coming to the sheets, your number of states are increasing, so charge carriers are increasing. As a result of that, you can increase the luminescence intensity there. So we are getting the longer decay time of the order of microsecond. We can also explain that from these natural laboratory calculations. So you can see basically the unaffected states are more delocalized both for singlet as well as triplet there. So this allows the charge carriers to stay more longer in the excited state, right? So that gives you the why we are getting such long luminescence lifetime in case of two-dimensional crystals. Then we changed the molecule a little bit. We started with the phenyl. Then we added two different fluorine groups here to obtain the diphenylpyridine here. Then if you change the ring of the phenyl ring position, you will have the benzoquinone. If you change again, if you add it here, you have alpha naphthol. If you add it here, you have beta naphthol. That means you keep the mother molecule same, just vary the functionality a little bit. So see, very interestingly, little bit change in the functionality is changing the two-dimensional structure here. So now we can readily form a long infinite molecular sheet by just changing this functionality here. And the thickness of the sheets is only 2.5 nanometer. And the area is over microns, right? Again, we have found the jump in the luminescence spectrum. But we can form different kind of structure. If you put a little bit of cadmium, you induce the heavy metal effect there. So you have the stronger luminescence. So the luminescence can be increased further by means of this heavy metal ion, retaining the same two-dimensional structure there, right? And you can prove the extent of the heavy metal by means of secondary anomalous spectroscopy. Okay, so this is consistent with that. Now see the other molecule, the benzoquinone. So these are forming small two-dimensional crystals. And you can align these two-dimensional crystals unidirectionally by means of this surface media. And all of these are highly giving luminescence. If you take the alpha naphthol derivative, you can form circular crystals, and these circular crystals can be merged into two-dimensional sheets with respect to surface motion. If you take beta naphthol, again, circular sheets are formed. You can merge into two-dimensional crystal. So that's a beauty. Small change in the structure. You can form a quite bit of large molecular sheet, which is semi-crystalline in nature. So using this high luminescence property, we started to show that some devices can form out of this aggregation-induced emission genes. So we formed the light-emitting diode using this region as Acharya. And this was a long time back report in 2017. So at that case, we found some quantum efficiency of 0.33, which is pretty low at that time. But the terminal voltage was around 3 volt, which is pretty good. Then now see, right? Readily we can go up to 2.5% of external quantum efficiency. Now, readily. So this gives you the opportunity to from the devices, and these are the photographs of the working devices. Again, the terminal voltage is around 2 volt, which is low for these organic systems. And we can tune the color of the light emitting diodes using different kind of AIGS there. So with that, it's a big thing, so not to be summarized. But the thing is that we can form one-dimensional assembly, two-dimensional assembly, also stacking into three-dimensional assembly using this technique on the water surface. So this gives you a platform to make different kind of devices, different functionalities, to explore different mechanism of luminescence. Okay, so we are still working on that. The what which I have shown is only part. Large sections are to be published in the queue. So definitely thanks to the funding agencies, which is particularly Department of Science and Technology, ACIB, of course, the synchrotron sources, particularly Photon Factory in Japan, Texas in Germany, solar in France. And thank you very much to all these collaborators who helped a lot with each other and rigorous theoretical calculations. Didi was involved from a long time back. There was a Milan Chanel was involved in all interfacial technique diffraction synchrotron. In our, he's the architect. He's designing some of it is there. While that also is supporting with the theoretical calculation. And these two guys, they're the architect for this all experiments. And with that, I thank you all for listening to me. Thank you.
Thank you, Professor Acharya, for this very interesting talk. The floor is open for any questions. I mean,
Need to see the YouTube if some things come. Chat box. Yes, we did. No, not DIOT. That the problem is those are in the supercrystalline image. So I mean, if I show that image, yeah, how can I make it smaller? No, you go to the shorter slide, slide shorter. Slide shorter. Here, from here I guess. This one. Yeah. So yeah, so this one all separated. But if you look at the structure here, these two black lines, which are the nanorods, and then if you see the next ribbon is situated exactly in the middle of the two nanorod. Yes, yes. So no, actually we tried not quite a few times. We tried because see, this is another image of a nanorod, right? So this is also a single nanorod. This is also STM image. This system we tried once or twice, not much, because our intention was to put the junctions, but we can do that actually. This is for the couple dot.
They're small. They're still states. Not for the neither do nor say you have a 1.3 nanometer, 1.3 nanometer by 1.3. That's a problem. We need to start growing. That can
Is-
take longer and longer and longer.
So it gives a spike light.
Make a spike, you have to make it quite.
Yeah. Because you have to allow that charge to go.
Okay, it's a confinement.
It's a confinement, right?
So how is it work? You just keep on adding.
Right.
Again, you have the rod. You put it side by side. How it goes from 1 to 1 to
Step like.
3 to 3.
Yeah, there are lots of theoretical calculation too, Alan.
Fine.
Is that? But
Many theories.
yeah, but following your point, I can mention one thing that it will be highly system dependent. I mean, the critical length where from you are seeing the transition from say to the spikes to the staircase. So it of course will depend on the material itself. Huh. It should be system. Right. Should be. Very good.
Does not go on to full 1 minute, without expire. You get a background which is 0.
Right.
Like a delta function. Which is not really there.
It's finite with. Yeah.
Without big part. Within that you will have. Flat nothing. Gradually.
Evolved of the spike. That's fascinating. But what I can
Calculator we told all the dimensional process of this. Because how it is going to be 0 to 1 or 0 to 1 to 2.
That's nice.
In every dimensional crossover, they have the density. That was our calculation.
That's nice. That's nice because I was thinking that okay, dimensionality effect is quite proven. Actually, we have a JAX paper somewhere with the PPS nanocrystals with defined dimensions. So there we probed the electron proton interaction. And we found that it highly depends on the dimensionality, Wang-Rai parameter. So technique, but it's really interesting to hear that this critical limit you have carried out. I'll see that. But for this case, I can say one thing. Dimensionality effect won't be working here because here the entire electronic property is defining by the interface itself. The properties of this individual quantum dot is lost once you have this junction. But I'm sure that what you have suggested before for the zinc sulfide nanorods, we can see that. It's interesting.
So in the I think in before this slide, I think you have shown that there is a tunability that you can tune the overlap between these two nanodots, right? How did you tune this overlap?
Pretty interesting. See, it's not arbitrary, first thing, because you don't know which are the facets they are interacting. First thing. So what you need to do first, you design the individual quantum dots. It can also happen that this might not be picture. The individual quantum dots are merging together and is giving shifting. First, you have to ensure that it is not individual quantum dot. So the reaction at the temperature at which you are doing this reaction, you need to find out. You take one individual component, change the reaction, see where they are merging. So you have to carry out the reaction for this coupling below that temperature to ensure that this individual component is not enlarged, right? So now you know that at which temperature I can form the junction. So that's the initial state of the junction where you are getting this transition. Now you increase the temperature bit. So the junction will be diffusing, right? So junction diffusing means so that's how you can tune that.
Thanks. The other question is related to the zinc sulfide nanorods. So there you form the nanorods at the water surface first, and then you use this maybe scooping of method to take it in on a TEM grid. So normally these TEM grids have a lacy carbon layer probably, which you have used for imaging. So does, and then you haven't tried it in situ annealing of these nanorods inside the TEM, right? How it happens? I mean, this growth or this elongation, does it happen only at the water surface or water air surface, or there it happens in the if there is any possibility of diffusion at the
See,
carbon?
I can tell three different cases.
Sorry.
That's exactly what I wanted to say, that in situ TM heating is not permissible. I mean, the system is very reserved, only few places they have. In situ, once you inserted the sample in TM grid, you need some kind of special fibers in the holder and to apply voltage or something. It's not there. IOP is there. Okay, but the system is like that. You have the wires within the holders, you apply voltage, you heat it and do that. Also now you can probe, even while doing the TM, you can touch the probes and you can do the transportation. Now these systems are there. And one system on the surface we have shown. The other one is that. The third one, what you are suggesting, you can even take it on the hot plate and heat it. You'll see the ligands will melt and the nanorods will coalesce. But that coalescence should be uncontrolled. It's not like two-dimensional. Maybe they'll form two-dimensional islands, small islands, but it won't be a large area two-dimensional.
Thanks for the
Yeah.
answers. Yeah.
Material management. Material means that how to transfer
There are two things. I don't know if the layer of graphene can form at the water interface. That's the first challenge. In this process is very simple. The transfer process will depend on the resultant area of the solid support and resultant area of your water surface. So scale up can be of course possible. That's the beauty of this technique. I mean, you can take even 1 feet by 1 feet substrate if you have such big water surface there. That's not a problem. Size is not a problem. It's scalable. That's why it's called a scalable technique. The only limitation is that you cannot form a bent structure. The structure is straight structure. That's the only limitation. Each technique has advantages, limitations. So it goes like that. Like no, actually, in that case, what will happen? No, it won't work. Won't work because the surface tension will be changing. Surface tension will be changing, and you won't have that kind of regular pattern.
after making, then you can actually bend the substrate.
But the problem is, I'm not sure that if the water and the sample interaction is so strong that the intact structure will remain on the surface. Maybe it will bend. No, the advantage is, oh, you are telling that substrate should be bended. That can be done. That can be done. Because because the advantage is once it is depositing on the substrate, the area, the number of molecules or nanomaterials transferred onto the surface, that will be filled immediately by the constant surface pressure. So you won't have the vacant area there. So bent surface, okay, is possible. Why not? It's possible. Yes, yes. For these nanocrystals, for nanocrystals is room temperature real. But for these AI agents, we have carried out up to 20K helium system. It takes long time. It already showed the phenomena up to 20K. People have tried to probe the electron proton coupling with temperature dependent Bell spectrum. So there's lots of literature there on the electron proton coupling, and they probed it by means of this simply Bell spectroscopy with varying temperature. Organic LEDs, why with the AI gens as active layer. Actually, is better. The commercial, I am telling, if you bake a simply LED bulb or something, you'll find a chip which is containing says 12 small active devices. There are several chips like that. I have collection from the local market. Those chips is very difficult to collect. By somehow I collected. So those are integrated within a bulb, and the efficiency is something like EQE is something like 0.3, 0.4 like that. Okay, so it's better. But again, how do we commercialize this? We're not finding companies who are working here, because all these companies are basically assembling these LEDs here, buying the chips from abroad, just assembling here. But those chips, I really collected those chips. It's beautiful to see that some are 12 by 12, some are 6 by 6, and it defines the wattage actually. There's a pike cell. There's a pike cells, right? Einar, we have deposited it in terms of some mask, micron. So you make it finer, you will have a small pixels.
Okay, if there is no more questions, then I would like to thank again.
Thank you.